Hi, in this video we're going to look at the notion or the idea of a position vector. In the last video we introduced vectors. Now we're going to take this a little bit further with the idea of a position vector. To begin with, we're going to look at an alternative way in which we can represent a vector. Now, as we said before, vectors have both magnitude and direction. Now, if a vector has a magnitude of 1, it's known as a unit vector and can be written like this. Now, unit vectors are parallel to the coordinate axes, and they're denoted by either I or j. I is a unit vector in the direction of the positive x-axis, so the horizontal one, and j is a unit vector in the vertical axis, like the y-axis. So a normal column vector can be written in terms of I and j. So for instance, if we take the vector minus 2, 3, that can be written as minus 2i plus 3j, because I've moved 2 on the horizontal axis, so 2 in the direction of I is going in the positive direction, so we're going to have to make it negative, so that's why it's minus 2. And we're going up 3, and that's in the positive direction, so that's why it's going to be plus 3j. So in general, if you've got a vector that's a and b, I can rewrite that in the form ai plus bj. And the magnitude of that vector is simply going to be the square root of a squared plus b squared, the coefficients of a and b. Of I and j rather. Vectors that are expressed in terms of I and j can be simplified in the usual algebraic sort of way. So if I give you that a is the vector 2i plus minus 5j, b is the vector minus I plus 2j, and r is a vector that is 3a minus b, we can write r in terms of I and j simply by substituting in. So I've gone and replaced that a with what the value is over here. I've gone and replaced b with that value over there. And now all I do is a bit of simple algebra on there, expand the brackets, collect the like terms, and I now have my new vector. If I'm thinking about a vector that's a multiple, then we can see that the vector 2i plus j fits into that line 3 times. And so I could really think of it in terms of being a multiplying factor, a scalar multiplying this particular vector. Here's a problem. xi minus 2j is parallel to 12i plus 6j. Find the value of x. Well, since we know they're parallel, we know that this vector over here is simply going to be some multiple of the vector that is parallel to it. So I need to try and find out what k is. Well, the I components must be the same. So in other words, the coefficient of the I on the left-hand side should be the same as the coefficient of I on the right-hand side. So 12 is equal to kx. We know that the j components must be equal. So we know that 6 is to equal 2k, 2 times that minus 2k. And so we can then figure out that k must equal minus 3. Once we substitute that back into equation 1, we can get that x is equal to minus 4. As I said at the start, we're dealing with position vectors, and the key thing to notice about a position vector is that a position vector is a vector that's based from the origin. It has its starting point at the origin, and it goes out to a particular point. So if we think of the origin as being at that point O, and we have this point A over here, then OA is going to be the position vector of the point A. It's showing its position relative to the origin. Position vector B, I'm going to label as little b, and that's showing the position of the point B from the origin. That then allows us to develop or figure out this vector that's running from A to B. And that is not called a position vector, the vector AB. That is called a displacement vector, and that's the type of vector that we dealt with in the first video. Now, we've got a formula over here that says AB is equal to little b minus little a. And if we think about that in terms of a little bit of algebra, we can say OA plus AB is going to be the same as the vector OB. And if we rearrange that, we're going to come up with this statement over here. And that's a really important result that we're going to use a lot. So here's some examples. We've got the points A and B are given by the position vectors 4i minus 3j and minus 2i plus 5j respectively. We want to find the vector AB. Well, we know that AB is simply going to be OB minus OA. So in other words, it's the vector OB, which is minus 2i plus 5j, minus the vector OA, and the OA was 4 minus 3j. We expand the brackets, simplify the terms, and there we have the vector AB being minus 6i plus 8j. We take a look at the next example. The position vectors of x and y in meters are given by this, minus 2i plus 4j and 5i plus 5j respectively. We want to find the distance between x and y. Well, if we're going to do that, we need to find the vector xy. So xy is going to be OY minus OX. Notice over here, I'm going from x to y, so y is at the end. When I do my calculation for this, I'm going to put the position vector of y first, and from it take away the position vector of x. So we just need to make sure that we use brackets around that second term, that OX term, because of the effect of the double negatives or the negatives on the elements inside the bracket. Expand that and simplify, and there we get the direction, the displacement vector xy. That's 7i plus j. All we have to do now is to find the magnitude of that, because magnitude is the distance between two points. And we're going to use Pythagoras there. We come up with our answer to 1 decimal place, 7.1 meters. Here's another useful application of the notion of a position vector. So we've got, from the previous slide, we've got this idea that the vector OB will be simply the vector OA plus AB. If I rearrange that, I'll get what the displacement vector AB is. But if they go and give you a position vector for A and a displacement vector for AB, you can work out the position of B. In other words, you can find out the position vector of that, because simply OB is equal to OA plus AB. So here's the example. Point A has coordinates 4, 2, and AB is the displacement vector 3i minus j. We want to find the position of B. Well, we can write the position vector of A as being 4i plus 2j. We know that OB is OA plus AB. We've got AB as a displacement vector, so all we have to do is substitute those in, expand the brackets, and collect the like terms. We now have the position vector of OB as being 7i plus j. So there's the position vector. If this was on a Cartesian plane, then we could say that the coordinates of the point B will be 7 along the horizontal axis, so in other words, and 1 on the vertical axis, so that would be the point 7, 1. Sometimes you might be required to find a unit vector. So here we have an example, find a unit vector in the same direction as the vector 3i minus 4j. So it's going to be in the same direction as the vector v, only difference is that its length, its magnitude, is going to be 1. So we first of all work out the magnitude of the vector v using the Pythagorean formula. So we get that the magnitude of v is 5. All we have to do then is to divide the length of v by 5, so in other words it's going to be 1/5 of v, and so the required unit vector is going to be 1/5 of 3i minus 4j. Notice there's a little convention here. When you're working with a unit vector, you put this little hat over the top of it. Another example might be this. Find the vector of magnitude 3 that's in the direction of 2i plus, let's say I plus 2j. So it would be useful to find the unit vector of I plus 2j. So we find the magnitude of that vector, and if we leave it in surd form, we can say, right, there is the unit vector for this original vector that we're talking about. Now, if we want it to be of magnitude 3 and in the same direction, all we have to do is to go and take that unit vector and multiply it by 3. This leaves us with a number that has an irrational denominator, so we can go and rationalize that denominator and we'll end up with this vector over here. Finally, we're just going to run through a couple of examples of this last type. So, ai plus bj is a vector of magnitude 4 units and in the direction of I minus 3j. Work out the values of a and b to 3 significant figures. So, we can find the magnitude of I minus 3j. Using Pythagoras, we're going to get it to be the square root of 10. Here is the unit vector of that direction vector I minus 3j. We know that it has magnitude of 4, and so that we can pick up that ai plus bj is going to be 4 over root 10 I minus 3j. If we look at the horizontal components, we'll come up with that number. If we look at the vertical components, we're going to come up with this number. And so we get the values for a and b. The second example, point C lies between AB and is 5 units from A. You've got the position vector of A as being 2i minus 5j, and the position vector of the point B as being 10i minus 11j. We want to find OC, the position vector of C. So, to begin with, we're going to find out the vector AB, the displacement vector between A and B. Well, we go and plug in the values of OB and OA, remove the brackets and simplify, and we get the vector 8i minus 6j. And we can find the magnitude of that using Pythagoras, and that comes up to being 10 units long. So there are the key features about this displacement vector AB, something they didn't tell us at the start. We've got the displacement vector, and we've got the magnitude of that vector as well. Now, let's say C is 5 units from A and lies in the direction of AB. So in other words, that is going to give me what the direction of the vector is going to be, and it's going to be halfway along the line AB, because 5 is half of 10. So all I have to do then is just simply go and plug that in, plug the values into the formula, and there we have the displacement vector AC. Once you've got the displacement vector AC, then you can work out the position vector of OC by plugging in the values that we know, the vectors that we know, OA and AC, and simplifying it. Always useful with these sorts of examples to have a little diagram as you're working through it. Right, what I'd like you to do now is to go and find the homework task for this position vector lesson and work on that, please. Thanks very much. Goodbye.